mechanism where it basically takes place in octagonal site where the electrons from Fe3 or any other similar metal it means conduct to Fe1, Fe3, Fe3 to Fe2 present in B side so that conduction of current takes place or electron gets conducted from one state and to state and the contribution is basically due to 3D electron. There are many applications of ferrite from recent applications to traditional applications, drug delivery, EMR, like sensors, and then the transformers, levitation, cancer treatment, recruiting, right? And then about spinners, spinners have high refractive index, so they are used in GMG stone as well. They are used in spin materials, in mobiles, laptops, etc. And they are also used as supermagnets in MRI and NMR. So the method we are going to adapt for its preparation is full auto-combustion method, where nickel nitrate, zinc nitrate, copper nitrate, ferric nitrate are taken as starting materials and they are mixed with each other. And finally, the resultant mixture is mixed with citric acid in 1:1 ratio. They are homogenized by continuous spinning and heating at 100 degrees centigrade for 4 hours. If the solution is not neutral, then we add ammonia and we test whether its pH value is 7 or not. Finally, we get neutral nitrate type solution, and this is how we call it salt. If we dry it for 40 hours at normal temperature, then it will take the form of gel. And that is why we are telling salt gel method. Now, the gel is auto-combusted in so that it gets burned and then turn into air. After gas and calcium in 800 degrees centigrade for 4 hours at the rate 5 degrees per minute, then we will get nanoferrite powder. The nanoferrite powder can be used in XRD and many other applications for testing samples. And if we want to study the electrical and magnetic properties, then we should have to make it in the form of pellet. For that, we can add polyvinyl alcohol and pressed under a die with the pressure of 5. Then we'll get pellet. The pellet is centered at 800 degrees centigrade in muffle furnace, and then we just polish its surface, and we polish with the help of gold, and finally we will make it as electrode. Then it will be used for the electrical and magnetic property study. So here, the composition we make, there are 4 compositions, different compositions of the copper. For experimental study, the first one is powder extracting method. Here, it helps to determine the structure of the material that we have prepared. We have prepared the materials in basically 5 compositions, concentrations of copper. Basically, the actual having 0.05, 0.1, 0.15, and 0.2. So here we see that the highest and the sharpest peak is in the direction 311. So this is useful for the determination of splice size that can be obtained from zero formula. And that parameter can be calculated from this relation, where D is interplanetary spacing and SCR are Miller relations. So when these data are tallied with powder diffraction stamp, then they match with single phase cubic spinner. The peaks are accumulated here. An overview of this peak shows that the maximum intensity peak is moving towards lower angle side with the concentration, with the increase in concentration of heat. Talking about splice size, due to the larger ionic radius of copper, that is 0.73 angstrom, that is going to replace nickel, that is 0.9 angstrom. The resultant lattice parameter is increased. As a result, the cell volume will also be increased. But about crystalline size, there are ups and downs in crystalline size, and that is due to different factors. Like strain is produced during the period of synthesis, and then there will be density of localized state enthalpy, site mismatch, mutation, etc. Then about scanning electron microscope study, it shows that the grain sizes are nearly equal and small, which are means it is indicating that they are prepared for microwave devices. The spectrometer that is attached with the scanning electron microscope shows that the composition of the sample is well, and this is the EDS figure is on here, where this is on the one. There is no copper, where the composition is exactly matched. So this is how EDS results. About FTIR spectroscopy, this helps to give the functional group, and the gap between transmission and wave number gives the fine region almost within 600 to 400. The region within 600 to 400 per centimeter is the region for spinal structure or a ferrite, and there is little bit shifting in the value of wave number, and that may be due to the change in bone length, which change the vibration, and the vibration is the effect. So about magnetic property, the coercivity and magnetic intensity is maximum at composition near crystal disease 1. So the magnetic property is affected by the concentration of metal ion on both octahedral and tetrahedral side. So the fluctuation here is due to the cation and exchange interaction. About the DC electrical resistivity, from this figure it clearly shows that the sample has negative temperature coefficient with resistance. If it has this type of property, then obviously this is showing the semiconducting property. So this is due to the hopping mechanism that I already told you. So due to hopping, what happens? The insulating ferrite is becoming semiconducting. This is quite interesting for us. We can determine the activation area. Here we can see the relation where this is resistivity. This is resistivity, maximum resistivity, or the exponential factor, and this delta E is the activation energy, T is Boltzmann constant, and T is absolute temperature. So from here, this electrical resistivity is
from here. Well, this is it's a minority.
And it's also should also be high, so that the conduction takes place, and the activation energy is the energy that is required in order for the whole mechanism. So here, similar to the previous slide, the maximum activation energy required is at 0.1. So, and overall energy found is 0.4 to 0.51. So finally, I came into conclusion. X-ray diffraction source is a single phase single cubic spinel. Lattice parameter increases with copper concentration due to if a larger effective ionic layer of copper. Ups and downs on crystal size is due to lattice strain during the period of synthesis and other factors. And same source smaller grain size, and which is relevant for microwave devices. FTIR source single phase spinel cubic spinel. Magnetization and coercivity is maximum at 0.1, and it has negative temperature coefficient with resistance, that is, it is by semiconducting nature, and finally, DC resistivity is copper activation. So, this is how I conclude my presentation. I want to acknowledge ANPA and other associated organizations from the side of my supervisor, Professor P. Samata. He is also the head of the department, and from my departmental research committee, and from my family member as well. So if there are any queries, please let me know. Thank you.
Okay, thank you, Dipendra, for a nice talk. I think we have time for very quick 1 or 2 questions. So I want to open the floor for any questions.
I have a question.
Yes, so any questions for our speaker?
I have one question, Sam, sir.
Yeah,
For
sure.
the speaker. I saw some extra data in his talk, and thanks for the talk, Devinder sir. I have one curiosity. Do you guys do refinement of the X-ray data and get some structure from the refinement, or you just look into the peak shape or peak movements for the temperature or with the angle dependence of the peak shift? Meaning that do you guys refine the X-ray data or not, and get the structure?
Looks Dr. Dipendra Parajali is not here, I guess.
Oh, okay.
He was here, right?
He is supposed to be in India. I mean, basically, physically, he's in India, but he was supposed to be online, but somehow he's not here.
He's not here. Yeah.
Yeah. Move to next.
All
No
right,
worries.
so then let's move to the next one. So our next speaker is Chandramani Adhikari. He is from North Carolina Central University. So today he's going to talk about the optical response of ultra-thin carbon nanotube films. Please, Chandramani Adhikari, take the stage.
For being here. I'm Chandra Adhikari. Today we'll be talking about dielectric response of aligned single-wall carbon nanotube films. This work has been done with Professor Igor Bondari. Our funding agencies are National Science Foundation and Department of Energy. Let us begin with what is a single-wall carbon nanotube. A single-wall carbon nanotube is a carbon allotrope in a cylindrical shape. If we roll up a graphene sheet into a 3D tube, then we are going to get a single-wall carbon nanotube. The dielectric response of a single-wall carbon nanotube is a function of the radius of the carbon nanotube and the photon energy, where we have expressed this photon energy in terms of 2 gamma naught, where gamma naught is the carbon-carbon nearest neighbor overlap interval. The real part of the dielectric response function controls the refraction. The imaginary part of the dielectric response gives us the exciton absorption spectrum, while the negative imaginary of 1 over epsilon gives the energy loss spectrum, and in our case, this is a +1 spectrum. Let us talk about a model of the single-wall carbon nanotube film. The carbon nanotube are aligned in a periodic manner. The area of the carbon nanotube is immersed in a dielectric medium of permittivity epsilon, which is sandwiched in between the substrate and a superstrate of permittivity epsilon 1 and epsilon 2. This is the thickness of the film. Length of each carbon nanotube is L. Delta is the center-to-center distance between 2 carbon nanotubes, and L perpendicular is the length of our film. When a photon is signed in a carbon nanotube, then the carbon nanotube gets excited. The carbon nanotubes talk to each other through the dipole-dipole interaction. We have derived our dielectric response function of the film using many particle distribution formalism, which has been presented in many particle physics textbook by J.D. Mahan. He has done that for completely different systems, but more or less the problem idea is the same. What we found is that the perpendicular component of the dielectric response is nothing but the background, while the parallel component of the dielectric response is the conductivity of a carbon nanotube. Sigma bar is the dimensionless form of the conductivity. It also depends on the incident photon, energy of the incident photon. It depends on the carbon nanotube plasma frequency of the broad electron gas. It obviously depends on which carbon nanotube we are using in the film. And it also depends on the volume fraction, means the volume available for a carbon nanotube per unit volume of the film. In this slide, we talk about a single wall carbon nanotube spectrum versus the spectrum of the film of carbon nanotube. For illustrative purpose, we take 11-0 carbon nanotube, whose diameter is about a nanometer. The diagram on the left is the spectrum of the dielectric response and conductivity of a single wall carbon nanotube. The response function has been plotted as a function of photon energy, and the photon energy is expressed in electron volt. If we check this window of photon energy, then we're going to have two exciton resonance and a plasmon resonance. By plasmon resonance, I mean that this is a real of 1 over conductivity, which is the solid gain 1, or negative imaginary of 1 over the dielectric response function, which is the test 1 over here. The inset over here is the magnified version of the response function versus photon energy plot near the plasmon resonance. The conductivity has been calculated using KP method of carbon nanotube penny structure theory, and the conductivity curves means the solid curves over here are scaled for better visibility. Now, if we take that window and if we do the same for an area of the carbon nanotube using the equation that we have derived and we discussed in the previous slide, the dielectric response function spectrum looks like as if we have shown in the right half of the slide. We take the nominal value of epsilon equal to 10 for the permittivity of the dielectric medium in which the carbon nanotube is immersed, and we say that our film is hanging on the air. This is what this epsilon 1 equal to epsilon 2 equal to 1 means. The thickness of the film is 20 times the radius of 11-0 carbon nanotube, which is about the 9 nanometer. And this FCN, that means fractional volume of carbon nanotube in the film, this depends on the D thickness and delta, that means the center to center distance of the carbon nanotube. And we can convince that these cannot be larger than pi over 4. And in our case, if we use the parameter D equal to 20R and delta equal to 2R, this FCN is going to be pi over 40. One interesting thing about the spectrum of the dielectric spectrum of the array of the carbon nanotube is that this is not only the function of the photon energy and the radius of the carbon nanotube like it is in the single wall carbon nanotube, but in the case of an array of carbon nanotube, it is also the function of the momentum, which makes this the non-local phenomenon. And the momentum is along the axis of the carbon nanotube. One more thing we can notice is that this plasmon resonance is more pronounced in the case of an array of the carbon nanotube than in the single wall carbon nanotube. And one more thing, you can notice that the photon energy for the exciton resonance is kind of like same for the single wall carbon nanotube and that in the case of the array. But the plasmon resonance, you can see over here, this has been shifted towards the exciton resonance. You can see that the plasmon resonance for the single wall carbon nanotube is about 1.5, but the same in the case of the array of the carbon nanotube is a little less than 1.3 electron volt. And one more thing, you can see that the real part of the response function is negative for the wide range of photon energy, This means that an area of the carbon nanotube can also be used as an hyperbolic metamaterial. Recently, these guys found experimentally that a film of self-assembled carbon nanotube has a tunable hyperbolic metamaterial behavior. We can explain this experimental fact by using the Maxwell-Garnett mixing of homogeneous arrays. What you do is the following. We take about a half dozen of the homogeneous array of carbon nanotube in which carbon nanotube are roughly of the same diameter. We mix them in such a way that the thermal average of the response function is the sum of the thermal average of response function of a homogeneous array of carbon nanotube times the weight of that homogeneous array. The weight has been assigned in such a way that the total weight is going to be 1. And what we found is that the spectrum of the response function is widely broadened. This negative refraction band, you can see that this is even wider than the negative refraction band for a single homogeneous 2D array. And we believe that this is because of this exciton-plasmon coupling that present in the inhomogeneous array of the carbon nanotube. This fact has been already published in Material Advances 2020. And if you are interested, please have a look on that publication, or if you want to talk with me, I'll be always happy to talk about that. Let me summarize what we talked today. The carbon nanotube film dielectric response can be expressed in terms of the complex longitudinal conductivity and the plasma frequency of an individual carbon nanotube. For homogeneous single-wall carbon nanotube films, the real part of the dielectric response function has negative refraction band, indicating that the film behaves as a hyperbolic. Inhomogeneous.
We shouldn't talk like that because it's because due to the influence of helium, due to the influence of helium in this,
the homogeneous carbon nanotube array
is becoming the worst.
Broadening of the exciton and plasmon resonance leads to their overlap, making the exciton-plasmon coupling and associated hybridization possible. Thank you.
Okay, thank you, Chandra, for a nice presentation. So I think we have time for a couple of quick questions. So I want to open the floor for a question for our speaker. Questions for our speaker?
Chandra Mani Bhai, I have one question. This is sorry. So this is a very interesting talk you presented about these carbon nanotubes. So in metal, basically, when you go to really small thickness, so dielectric function, usually loss function, is kind of inverse of the radius. So is there any direct relationship with the size or diameter of this carbon nanotube?
There is a weak relation. Yeah, we say there's a relation, but the relation is pretty weak because when we make an array of the carbon nanotube, I mean, if we just talk a single carbon nanotube, it's going to be exactly what you just told. But if we take an array of the carbon nanotube, then there is going to be the combination of many terms. That is going to be some sort of like the linear kind of relation that you just said. It's going to be kind of like complicated, but still there is going to be a little bit of that one, but not like in the metallic kind of like the cylinder, so to say. Like, yeah, I think if I understood correctly, I answered your question. I don't know.
Yeah, sure. Thank you.
Okay, so maybe we can have one more question. If not, thank you, Chandra, for a nice presentation. So we want to move to next speaker. So our next speaker is Dina Mikkel. She is from George Mason University, and the title of her presentation is Tuning Topological Properties of Chemical Substitution. Topological Properties by Chemical Substitution. in cobalt and niobium selenide, sulfur-based compounds. Dina, please take the floor.
Hello, my name is Dina Michelle, and I'm from George Mason University. Today, I'll be speaking about the effect of chemical substitution on the anomalous Hall effect of the chiral lattice antiferromagnet cobalt niobium-3 sulfur-6. To begin with a little bit of background, it is known that every conductor shows the Hall effect. When magnetic field is applied perpendicular to current and voltage is measured across both, we get the Lorentz force, which is responsible for the Hall effect. The ordinary Hall effect is given by the Hall resistivity rho yx, which is equal to R naught mu naught h. In this case, shown right here, the Hall resistivity is linearly proportional to magnetic field. In ferromagnets, the Hall resistivity picks up an additional component that is non-zero even in zero magnetic field, hence the name anomalous Hall effect. This additional anomalous term, given by rho anomalous yx, is proportional to magnetization. In the bottom figure, it is shown right here in a soft ferromagnet and in a hard ferromagnet with a clearly pronounced hysteresis. Additionally, there are other mechanisms that can give rise to the anomalous Hall effect. It has been shown that the anomalous Hall effect can come from non-coplanarity in ferromagnets as well as non-collinearity in antiferromagnets. Anomalous Hall effect arise also from mechanisms such as complex magnetic textures. For example, here we have skyrmion, as well as from topological band structures such as those in bial semimetals. Recently, the anomalous Hall effect was shown in cobalt niobium-3 sulfur-6, which was shown to have a collinear antiferromagnetic structure, as well as a lack of a center of symmetry. The anomalous Hall effect in this material was not expected since collinear antiferromagnets were not known to give rise to the anomalous Hall effect. And continuing further with background information on cobalt niobium-3 sulfur-6, the parent compound used in our study, the susceptibility here shows magnetic transition at 27.5 Kelvin. Additionally, complex behavior was shown when field was applied along the z-axis. And on the right is the electrical resistivity, which shows the nail temperature also at 27.5 Kelvin. Finally, here is the Hall effect that was shown in cobalt niobium-3 sulfur-6. When comparing the plots of magnetization and Hall effect, we see a small moment right here in contrast to the comparatively large Hall effect. This Hall effect was shown to be linear above the nail temperature, and as temperature was decreased, the anomalous Hall effect could be seen. Now, since collinear antiferromagnets were not known to give rise to the anomalous Hall effect, one scenario that was proposed to explain the observations was that maybe this behavior came from the band structure. In the center is a part of the band structure that shows the vial node at the gamma point very close to the Fermi energy. On the right is a figure of the Hall conductivity versus chemical potential. What it tells us is that in a chiral crystal such as cobalt niobium-3 sulfur-6, where certain symmetries are lacking, the Hall conductivity is sensitive to the location of the chemical potential, Fermi energy. So the sensitivity observed in cobalt niobium-3 sulfur-6 could in part be related to this. Therefore, if the proposed scenario is true, that the anomalous Hall effect observed in this material came from the band structure, and that the Hall conductivity is sensitive to the location of the Fermi energy, it would follow that chemical substitution could affect it. And since the Fermi energy is very close to the vial node, we should be able to tune it by doping the parent compound cobalt niobium-3 sulfur-6 and then observe the changes in the band structure. This idea was the basis of our study. What we did was dope cobalt niobium-3 sulfur-6 at the cobalt sites. We first doped with iron in order to add holes. This was expected to lower the Fermi energy, as shown right here. We then also doped with nickel, adding electrons, which was expected to push the Fermi energy further up into the electron pocket and farther away from the vial node. Our crystals that we measured were grown via chemical vapor transport. And on the right, you can see an image of some of our 10% iron dope samples. We start with the properties of the 10% iron dope sample. First, we have the magnetic susceptibility, which shows similar properties to the parent compound. with a magnetic transition temperature in the same range as the parent compound, telling us that the introduction of the iron did not change the magnetic behavior of the material. We also see complex behavior in the field-cooled measurement when the field was applied along the z-axis, just like in the parent compound. In the center, we have the electrical resistivity, which also shows similar properties to the parent compound, shown right here in the inset. And this further confirms that the Néel temperature is in the correct expected range as in the parent compound. And finally, on the right, we have magnetization, which also shows similar behavior to the parent compound. The magnetization was measured here at 3 Kelvin and at 27 Kelvin. At 27 Kelvin, it is linear with no hysteresis, but at 3 Kelvin, we see a very small hysteresis, meaning that there is a small ferromagnetic moment present. Here we see the Hall effect in our 10% iron-doped sample. And for comparison, I have inserted the plot of the Hall effect in the parent compound. The total Hall effect retains the same behavior, as we can see, but what's interesting is that the anomalous part in the center of each is different. It has flipped direction. Now looking more closely at the plot on the left, we see that at 27 Kelvin, there is a large Hall effect, but that at 2 Kelvin, there is no Hall effect. If the behavior was proportional to the magnetization we saw on the previous slide, which was linear at 27 Kelvin and had a small hysteresis at 3 Kelvin, we would expect a larger anomalous Hall effect at 2 Kelvin over here than at 27 Kelvin. But what we see is the exact opposite. This tells us that the Hall effect does not come from the ferromagnetic moment that is present, and that it must in fact come from somewhere else. For clarity, here are plots of only the anomalous Hall effect, which we obtained by subtracting the linear part from the previous slide. We can clearly see that the anomalous Hall effect in the doped material has changed sign and flipped from the undoped compound. What this means is that the Fermi energy has moved down from the electron pocket and down into the hole pocket, and this is because of the holes we added when we doped with iron. Then the band structure responsible for the observed anomalous Hall effect is above Fermi energy, as shown right here. Next, we doped cobalt niobium 3 sulfur 6 with a small amount of nickel, 5%. What we observed was that the magnetic susceptibility and the electrical resistivity retained similar behavior to the parent compound and had a transition temperature in the expected range, showing that the nickel did not change the magnetic behavior of the material. However, we see a significant change in the Hall effect. The anomalous component is completely killed off. What happens here is that due to the introduction of the electrons from the nickel, the Fermi energy is pushed up further into the electron pocket away from the node, further lending support to the idea that this anomalous Hall effect comes from the band structure. Taking our result into consideration that the anomalous Hall effect can indeed be tuned by chemical substitution, the question then becomes, can we quantize the Hall effect in this material? Looking at the figures at the top here, we can see that it has been shown that the Hall conductivity attains 60% of the quantized value in thin flake cobalt niobium 3 sulfur 6, which shows the same Hall effect as in the bulk crystals. And what we have done here is that we flipped the sign of the anomalous Hall effect through doping, which means we've moved the vial node below the Fermi energy to above the Fermi energy. Then the idea becomes, if we can dope cobalt niobium 3 sulfur 6 with the optimal amount of iron and put the vial node right at the Fermi energy, the anomalous Hall effect will quantize. In summary, what we can control the anomalous Hall effect. We dope it with iron, the energy below the vial node, sign of the anomalous Hall effect. And by doping with nickel, we introduced electrons which raised the Fermi energy further up into the electron pocket and away from the vial node, killing off the anomalous Hall effect entirely. We tune the anomalous Hall effect by a chemical substitution. The likely scenario is that this anomalous Hall effect is indeed coming from the topological bands close to the Fermi energy, since we were able to change the location of the Fermi energy by chemical substitution. And this brings me to the end of my presentation. Thank you to ANPA, and thank you to everyone watching.
Okay, thank you, Dina, for a nice presentation. I guess we have a few minutes for a couple of quick questions. So if you have any questions, yes. Dr. Gimire, please go ahead.
Thanks for the nice talk. So my question is, you talked about, by introducing doping, you move the Fermi level up and down, depending on what type of doping, you were able to choose, moving up or down. So I'm wondering, what is the effect of doping on the wild node itself? For example, do you expect that you actually open up the gap as well by the doping, and whether or not your measurements are sensitive to the opening of the band gap?
I'm actually not certain of the answer to that question. I just know that the band structure that I inserted in the slides is calculated in the paramagnetic state, but beyond that, I would have to double check before getting back to you.
Okay, thank you.
More questions?
Hi, Dina. I have one question for you. Thank you for the nice talk. I have one curiosity, like once you dock with nickel to your parent compound cobalt niobium S6, so like you said, there is no change on the magnetic structure or magnetic properties by doping with nickel, yeah? Does it mean how these, like the movement of nickel diluted, like on your compound, does it has no effect to the magnetic properties?
So the transition temperature remains in the same spot, but if I could have gone back to the slide, I would show that the in particular case of the nickel, there is a little bit more noise as a result of the smaller moment. So it does affect it, but it just does not change the behavior in terms of the transition temperature and the Hall effect, and aside from the way that we were expecting.
Oh, okay. One more quick question. Like how this the movement of wild node affect the how this is related with the anomalous Hall effect? I'm sorry, I don't know much about it. Like the from below the Fermi surface and above the Fermi surface, how this is related to the anomalous Hall effect?
Sure. In this case, in the case of the Weyl node, the linearly crossing bands, they act as monopoles, and those have the Berry curvature, and then the electrons, as they move around that, they pick up the Berry phase that causes the anomalous Hall effect that we were able to observe.
Okay. Thank you.
Thank you.
Maybe one more quick question?
Yes.
So if you don't have any questions, then I actually have one. Okay, Dr. Gimire, go ahead.
I just wanted to follow up to that. If you didn't have let's say the monopole is already broken, for example, so even in that case, just from the asymmetric carriers, as you said, when you move the Fermi level up or down, won't you still expect the anomalous Hall effect like behavior even without monopoles?
In this case, I'm not certain. I'll double check and
Okay.
come back to you.
All right, so if there are no more questions, then I'd like to thank Dina again for a nice presentation and all the listener and all these questions, good questions. So we'll move on, and our next speaker is Dipendra Dahal. He is from North Carolina Central University, and today he is going to talk about effect of strain on plasmons, screening, and energy loss in graphene substrate contacts.
I couldn't play his PowerPoint. Can anyone help me? Hello?
Who is that now, Neil?
Dipendra Dal.
I can do that. Can you make me
Yeah, sure.
please?
Your name is your CR, right?
No, that is my cell phone. Okay, I will take a host, by the way. Okay, I can do that.
Okay. Okay.
All right. Do you see my screen, Neil?
Yes.
Okay.
Yes. Mm-hmm.
Is that playing?
No, not yet.
Okay.
We can see your screen, but
Okay. Huh.
I can play it. I mean, Chandra Adhikari can play it if you still have
Yes,
it.
go ahead, please.
Could you please make me the presenter?
Okay. Yes. Yeah, you should be presenter now. Please go ahead.
See the content on screen.
mm-hmm.
Yes, you're good.
Yes, yeah, it's good. Yeah.
This is me, Dipendra Taha. I'm doing postdoc research here in North Carolina Central University. So today I'm going to present my talk on effect of strain on plasmons, screening and energy loss in graphene substrate contact. So I did this research with Professor Godfrey Combs from Hunter College Clinic in collaboration with Dr. Dan Hong, Air Force Research Lab, New Mexico. Here is the outline of my talk. I'll briefly give you the introduction. I'll briefly describe the theoretical model and present my result and discussion. And finally, I conclude my talk with. So in the system, so when a charged particle GE run over the structure with certain velocity, then it loses some energy. So what is that energy loss that we will show? And beside that, I will calculate the surface response function of this structure. So the potential for different region, are shown here on the left side of the slide. So there are several coefficients, and the important one is G Q parallel omega. So this G Q parallel omega is the important coefficient which gives us different condition for getting the plasma mode dispersion relation. So the graphene, when it is kept on the substrate, it gets strained. The Hamiltonian of that strain graphene gets changed. The Hamiltonian becomes S bar df sigma q parallel q prime. So, and the effect of strain causes the change in the Hamiltonian. The important effect is the energy band structure gets changed. So because of that change, because of that modification in the energy band structure, the polarization function of the strain graphene is little changed. So we have up to the second order correction. The polarization function is shown here in the left bottom of the slide. The polarization function is little changed up to second order correlation function, up to second order. So because of that correction, the polarization function for different condition, for different value of the parameters shown in the slide is given here. So in slide A, we have constant polarization value for different strain. So when we have no strain on the graphene, the blue line shows it is constant up to twice K Fermi, and it increases monotonically. But when we increase the strength in graphene, the value of polarization increases slightly. Now, the first figure, A and B, they are the polarization function when we have only first order correction. Now, the lower C and D, the figure C and D, they are the polarization function when we consider second order correction. So the difference is that at twice K Fermi, because of second order correction, there is some similarity at twice K Fermi. Besides that, everything else is almost similar. Okay? And on the other side, the figure B and D, the polarization function for any value of the strain angle. So it's done for strain angle. For any value of strain angle, the initial value is same. Up to twice K Fermi, initial value is same for all, but the difference is when it go above, when the wave vector is above twice K Fermi, the difference is seen there. The blue line in all the figure is for on-strain graphene, and the other dashed line they are for strain graphene. This is the value. This is the change that we see due to the strain. So using the set of equations that I presented in the initial slide, I calculated the G-response function. This G-response function is so strong that it gives the plasma mode dispersion condition for any kind of combination of 2D layer and the substrate. So for the given combination of 2D layer and the substrate, the G-response function is shown here on the left top. And for another case, when the sheet is just above the substrate with some distance in between them, the G-response function is shown on the right side. So I'll discuss in detail about the use of this G-response function on the coming slide. Now, so I'm going to discuss about the same figure that I showed you previously in the beginning of my discussions. So here, for this given structure, when there is no phonon, when the phonon coupling is absent, we have two pairs of plasma dispersion relation. One originating from the origin, and the other two originating from the bulk plasma frequency. So this in the upper one is due to upper two or upper pair is due to the substrate effect. It's nearby the bulk plasma frequency, and the lower two is due to the presence of the two graphene sheet. And in the figures in figure B, we have shown the effect of phonon. The effect of phonon is the phonon coupling caused the origination of two plasmon mode in the middle originating from 0.5 of plasma frequency, half a plasma frequency. So this is due to the plasmon phonon coupling. A similar effect is seen when we consider gap graphene. So when we have gap graphene, the particle mode excitation region gets split into two parts that we can see here in the figure. So when we increase the band gap, the splitting widens, and because of that gap widening, the plasmon mode survives in the larger wave vector region. And the effect of the plasmon phonon coupling is the origination of the new plasmon mode pair that is in between the two pairs. One is acoustic and the other one is near optic hybrid optic mode. Now next we see the effect of strain. on the plasma mode. So basically, figure A does not have strain, and figure B has the strain. So the effect that we see here in figure A and B is figure A, the plasma mode, the three pairs of plasma mode, they are all similar. The only distinction that we get is when figure when we consider strain, the two plasma, the upper hybrid mode, they get in contact. So we get a kind of degeneracy there. That is the big difference that we get due to the effect of strain. So next, we calculated the energy loss when the charged particle runs over the graphene sheet, uses some energy. So that loss in energy we calculated, and the difference for strained and unstrained graphene is shown in the figure. So basically, in the lower velocity region, we didn't see any much differences. But as we go on increasing the kinetic energy of the charged particle, then the effect of strain is significantly seen. So for larger velocity, the effect of strain is, the rate of energy loss is very high in comparison to the unstrained graphene. That is seen in both figures. So thus, I want to conclude my talk. The application of strain on graphene deforms the lattice structure that caused the change in the energy band structure, which led to the creation of band gap. The change in direction of strain can also cause the change in plasma frequency. The combination of the substrate and the graphene layer can be arranged in such a way that the plasma with the required frequency can be generated. So two other separate branches of plasma can be created by suitable choice of substrate with considerable lattice diversity. So, thank you. This is how I conclude my talk. So if there is any question, please ask.
Okay, thank you for the presentation. So I think we have time for a few quick questions. Speaker. All right, so if there are no more questions for our speaker, I have actually one kind of very naive question. So you said a gap graphene. So how do you open the gap in graphene?
So the general process of, are you listening me?
Yes.
Okay. The general process of opening the gap in graphene is by doping, and sometimes sometimes when we put the graphene on substrate or superstrate, then there is also the chance of band gap opening. And here in my case, when we apply the strain, we see a tiny gap originating in between the conduction band and the valence band. So these are the few method of creating band gap.
So you talk about strain. So that strain, if I believe, is when you put a graphene on substrate, that's where you get the strain.
Yes.
So in terms of that strain, so this is basically somehow related to lattice mismatch. So what kind of lattice mismatch is good, or is there any rough estimate that if you have this much of lattice mismatch, then you open this much of gap? Is there anything like that?
So the range of strain, that should be around 20%, like 0.2 of that value. And we generally put the substrate that we can use is hydrogen bromide. So these are the things that we use. And besides that, the mechanical strain can also be applied in changing the lattice structure. So these are some things that we can do to get band gap, and the created band gap is very small in value.
Okay, thank you.
So you're welcome.
If there are no more questions for a speaker, then we want to move on. Thank you for a nice talk. So our next speaker is Firoza Kabir, and C is from, I don't know, it's here, C. Anyway, Firoza is from Dr. Neopane's group at University of Central Africa. The title of the talk is Observation of Topological Surface States in Gadolinium Doped Antimony Stellarium Compounds.
Neil, so you wanna?
No, she's presenting.
Oh, she's live?
Yeah.
Okay, so I think we need to give her the presentation permission.
Now she is presenter. Yes.
So I was informed. Hello, can you hear me?
Yes. Yes.
I was informed my recording will be presented here, so I sent a recording to you guys.
Hiroza, we can do that. Okay, let me do that. Okay, Neil, did you get it, or you want me to play?
Yeah. Yeah. You need to play. Or Chandra.
Okay, I will play that. Do you see my screen?
Not yet.
How about now?
Yes. Yes. Now. Yeah. It's good.
Okay.
Hello, everybody.
Going good?
Yes.
We have used PPMS and VSM experimental techniques to find the transport and quantization properties. Can you play it from the beginning?
Yeah, from beginning.
Right.
Okay. Just sorry. Let me do that. Hope you see my screen, right?
Yes.
Firoza Kabir.
Hello, everybody. Good afternoon. I am Firoza Kabir, a graduate student from Dr. Madhavni Penny's group at University of Central Florida. Today, I'm going to talk about the presence of topological surface state in gadolinium-doped Sb2T3. So the main idea of my topic is how gadolinium dopants can modify the electronic structure of pristine antimony telluride. Basically, we have introduced this dilute 4f electron magnetism into pristine antimony telluride by gadolinium doping. We have used PPMS and VSM experimental techniques to find the transport and magnetization properties of gadolinium-doped antimony telluride. Additionally, we have measured the topological properties of the system by ARPES and time-resolved ARPES technique. Since antimony telluride is a topological insulator, in the further sections I would also like to discuss some basic concepts related to topological insulation. So the main idea of the experimental technique is nothing but the basic concept of photoemission process, which is photon in and electron out process. So when the photon hits the metal surface, electron comes out, and with the help of analyzer in the ARPES system, we are able to find the electron's binding energy, momentum, k-space mapping, Fermi surface, and band structure. This is our ARPES system and time-resolved ARPES system at UCF. By combining this laser and synchrotron as photon source, we get high-resolution band structure. You can see some of the ARPES measured Fermi surface and band dispersions here. Since a conventional RPS system has some limitations, like it can measure only the occupied electronic states below the Fermi level. So if you want to find the fascinating features of material in the unoccupied or non-equilibrium states, you need time-resolved RPS. So this is the experimental setup of our time-resolved RPS at UCF. So you can see in time-resolved RPS, pump pulse is employed to excite the dynamics in material, and probe pulse is used to image the transient electronic structure, which you can see in here. This is a dispersion map taken by our time-resolved RPS system, and here you can see some electronic structure above the Fermi level. As we mentioned before, that we have measured the physical properties of the gadolinium-doped antimony telluride, and we measured from Dr. Goffwick's lab at Idaho National Laboratory. And you know, the PPMS is good for measuring the specific heat, then magnetization, electrical and thermal transport properties of any system. Also, it is equipped with the VSM system, and this system is used for magnetic sample characterization, and VSM option actually transforms this PPMS into a sensitive DC magnetometer for fast data acquisition. So in this figure, it shows the temperature dependence of electrical resistivity, which actually have a typical metallic behavior in the whole temperature range. And this inset shows the magnetoresistance of the sample, where magnetoresistivity is relatively small, around 3.5%. Interestingly, at low temperature, the resistivity data shows a weak anomaly at around 2.4 Kelvin, which might suggest the presence of like long-range antiferromagnetic ordering. We have also used the magnetic measurement together with the EDS study or energy dispersive spectroscopy studies to determine the level of GD content in our system. So this figure shows the temperature dependence of the magnetic susceptibility with the applied magnetic field parallel to Z-axis. This inset shows the field dependence of the magnetization at various temperature. From the fitting of this graph, we got the GD content to be 0.9%, which is very close to the value of 1% that we got from our EDS data. So although antimony telluride is itself a diamagnetic material, a characteristic Curie waste temperature like theta equal to 0.19, which we got from the susceptibility data, this suggests the possible tendency towards antiferromagnetic interaction among the GD spins in these materials. Now, before starting to discuss about the topological properties of our system, let's get some basic ideas of topology. So what is topology? You can see a coffee cup here, and it's turning to be a donut, and also a ball which is turning to be a cow. So what's the basic common things in these stuffs? So this coffee cup and donut have one hole common in them, and this cow and the ball has no holes in them. That means if you continuously deform or twist these objects, their topological properties would be the same. So there are some basic concepts related to topological properties. If I get time, I'll say it later. So in condensed matter physics, topological insulator is very important concept, where it is defined as the a quantum material with a bulk band gap like an ordinary insulator, but they have this kind of protected conducting states on their edge or surface. And there is a spin momentum locking, so the spin polarized electrons can move through the surface, and there is a band inversion between the conduction and the valence band as a result of the spin orbit coupling. So there could be a formation of Dirac cone in topological insulator. In our current system, we have this kind of Dirac cone. So that could be possible in between the conduction band and the valence band. This kind of crossing is called the Dirac cone of this topological insulator. So the crystal structure is shown here, which is a hexagonal crystal structure with this 3D Brillinger of this GD-doped antimony telluride. From the DFT band structure calculation, you can see a direct band gap of around 0.18 eV at the gamma high symmetry point of the Brillinger. So the whole valence band here, this is robust against GD doping, whereas the well localized GD4F states produce a flat GD4F band here. It cuts through the conduction band here and hybridizes with this electronic-like conduction band. This shows the Fermi surface and the electronic structure of our sample. So a circular shaped hole-like feature is observed at the gamma point, which is the position of the topological surface state, and the enlarging shape of this with increasing binding energy confirms the hole-like nature of the band around gamma. So this figure shows the photon energy and the temperature dependent dispersion map along K gamma K direction. We observe one hole-like band, the blue dotted line, this hole-like band crossing the Fermi level, but we could not see it from the ARPAS data since ARPAS could not measure the position of this on the electronic structure above the Fermi level. So this so we would find the position of this Dirac-like state by using MDC curve and time resolved ARPAS in the next slides. And this one shows the temperature dependent dispersion maps. So these dispersion maps actually confirm the robustness of the surface state at different temperature. As we have discussed before, the hole-like band is crossing the Fermi level. So we wanted to find the position of the hole-like band above the Fermi level. So what we did is we extrapolate the Dirac cone from the MDC curve and found the position to be 160 MeV above the Fermi level. So this is a comparison of the primitive antimony telluride and the GD-doped antimony telluride. You can see easily the gap is narrower at GD-doped antimony telluride compared to the parent one. We also confirmed the Dirac cone from the time resolved ARPAS data. You can see the band dispersion at delay time -0.4 picosecond, where there was nothing in the above the Fermi level, no electronic structure, but at 0.7 picosecond, we see some like feature here, which confirms that there is a Dirac-like cone above the Fermi level. So basically, we have used detailed the transport, then ARPAS, time resolved ARPAS, and DFT calculation to study the electronic structure of this GD-doped antimony telluride. And Our magnetic and transport measurement presents GD doping to have some local magnetic moments with reverse-like behavior of the magnetic susceptibility and shows some indication of surface magnetic ordering at around 2.4 Kelvin. We observe some Dirac-like features, and the position of the Dirac-like feature is around 160 MeV above the Fermi level, which has also been confirmed by the time-resolved RPS. So finally, we could show that adding small amount of gadolinium introduces dilute magnetism into our system, and it doesn't prevent the formation of Dirac states in a wide temperature range. So we're basically funded from the NSF, then TT from DOE project and the Air Force project. This is our Professor Dr. Newpen and lab mates and our collaborators for this project. Thank you.
Thank you, Firoza, for a nice presentation. I think we have time for a couple of quick questions. Okay, questions for Firoza?
Yeah, I have one question.
Yes, absolutely. Please go ahead.
So, if there is a intuitive explanation of how this doping from GD is, introducing at least narrowing the band gap, because the atomic number is not very different from both antimony and tellurium, right? So I guess I'm a little bit surprised that given that atomic numbers are very similar, it is actually working really well. So do you have any intuitive explanation on how the doping is actually shrinking the gap?
So can you hear me?
Yeah.
Okay, so actually here is the doping was very small amount. I mean, there was very low concentration of GD atoms in our compound, but even after that, it introduces the dilute magnetism and it compensates the N-type doping from vacancy and anti-side defects. So that's the one of the main reasons. That's why we saw some doping effect in the transport measurement and also from the RPS and the band structure measurement.
Yeah, so I guess I was looking for something easy for for even outsider to understand. So what is the role of the doping on spin orbit coupling? Does it actually introduce the band inversion?
Yes, it has the band inversion because from you saw the antimony telluride band structure. If you have already seen the surface structure, you can see the band inversion. But here we were not able to do the surface calculation because of like 500 atoms calculation. It was a supercell calculation. It was so expensive. And so we can actually understand from the band structure comparison, bulk band structure comparison, that if you even doped with the GD, it doesn't affect that much to all the band structure, but there is a little bit gap reduction in between the whole band and electron-like band, which are closer to the Fermi level. So we can, confirm from the band structure that even if you put a little bit GD, it can make the band gap closer.
I see. So it is basically enhancing further the spin orbit induced band inversion. Okay, thank you.
Okay, I think at this point we don't have time for further questions. If you have questions, please post in the chat box, or maybe you can have a conversation with Firoza. So we'd like to move on, and at this point, I think we are the we are almost about done, except one last presentation, and our last presenter is Ganesh Pokhrel. He is from University of Tennessee, and his title of talk today is Inelastic Neutron Scattering Study of Lacunar Spinel Gallium, Vanadium, Sulfur containing compounds.
My name is Ganesh Pokhrel. I'm not hearing the, sorry, I'm the presenter, but I'm not seeing the exact presentation which I said. So do I start myself or the video is gonna play?
Yeah, you can start if you want.
Or I have like, I mean, I have the even YouTube. I send in YouTube, so very easy access. So I can just play the YouTube if you give me the access, or you can just play the YouTube videos too. Just that was
This is the YouTube video that you sent, right?
Yeah, that was. I saw the link there before.
Yeah.
When.
Okay.
Maybe you can make him presenter, and then you're gonna do that from his screen.
Yes.
Yeah, if you give me the access, I can just present now myself.
Okay.
Yeah.
Yeah. Okay. Let him give whatever he needs, and then he's ready to go.
Okay. Go ahead.
Yeah, please.
Let me share my screen first. Okay. It looked like I have this one here. Let me, I mean, I saw the YouTube link here, so let me play this.
Ganesh sir, you have to go
Yeah,
for
sorry.
the video mode.
I'm sorry. Say again.
So when you do share content, you need to select optimize for motion and video. Then that way sound will come.
How can I do that?
Go to
share.
Yes.
I'm sorry.
Go to share.
Yes, share.
Then click the share. There is share content.
Yep.
Can you see optimize for text and images?
Optimize for text and image. Yep.
If you click that drop down menu, you will see optimize for motion and video. Click that.
Optimize for motion and video. Yep.
Yes. Now it should work.
Okay. Should I start from the beginning?
Yes. You use the start. You use the start.
It's my. Oh, I didn't see it. This is not my screen. Okay, let me start from my the presentation. It doesn't look like the video is working now.
Yeah.
Is it working? Oh, okay.
This is not your screen, so.
Are you seeing my screen now?
Yes.
Yeah.
Okay, let me go through the screen if so. I didn't see the video is working properly.
I can try it for you, Ganesh, one more time.
Okay. Hi everyone, my name is Ganesh Pokhrel and I am a postdoctoral research associate at University of California, Santa Barbara. The title of my talk today is Spin Excitations in Multivariate Skyrmion Host GAB4S8. This work was done at University of Tennessee in Oak Ridge National Laboratory when I was a graduate student at University of Tennessee. I want to thank to all my collaborator who has a great contributions to continue this project before I go into detail about my presentations. Most of my collaborators, they are affiliated to University of Tennessee, Oak Ridge National Laboratory and Niche Center for Neutron Research. Meantime, I want to thank to my funding provider, Gordon and Betty Moore Foundation and Department of Energy Office of Science for their support to continue this project. These are the outline of my presentation.
Just make sure, it is going good.
Yeah, the screen look good, and I'm hearing. For me, it looks very good.
Okay, thanks.
First, I will briefly talk about the Lacunary spinel structure and the formation of new molecular cluster in these materials. Then I will enter into the material which I'm gonna present today, that is GaB4 acid, and then motivation behind it. I will talk about the synthesis procedure of this material and then the measurement detail and the visualization of data coming from the inelastic Newton scattering measurement. And then finally, I'll conclude with few concluding remarks. Basically, the Lacunary spinel structure is formed by the normal spinels with chemical formula Am2X4. The absence of alternate A-side metal ion in normal spinels that rearrange the M4 tetrahedral cluster, resulting a periodic expansion and contraction of tetrahedra, forming a Lacunary structure. In Lacunary spinels, the bond length between the magnetic ions in small tetrahedra, that is small, due to which the magnetic ions, the d orbitals, they overlap with each other, forming a molecular cluster. In case of GaB4 acid, there is a single spin which occupy a triply degenerate T2 molecular orbitals. As a result, this material is highly orbitally active, resulting orbital ordering at low temperature below 42 Kelvin. For the orbital ordering, the material elongate along the high symmetry 111 directions. As a result, the triplet degenerate T2 orbital splits into doubly degenerate E and non-degenerate A1 orbitals. GaB4 acid is attracting attention these days because of the rich phase diagram. Although the material has non-chiral polar crystals, it exhibits Scormion structure, which was theoretically predicted long time ago, although it took some time to observe experimentally the Scormion lattice in non-chiral structure. You can see in the slide that these material host multiple magnetic ground state, including nil type scormion, cycloidal ground state, and conventional ferromagnetic ground state. Although there are certain literature available in the market which talk about the static structure on these materials, but there is a very limited work which explain about the dynamic structure. The absence of such studies is due to the inability of having larger single crystal of this material which scatter in inadequate amount of newtons, giving showing some dynamic structure in the system. So my motivation is to look into the dynamic structure to understand the spin interactions between the neighboring magnetic vanadium ion. Now we have the motivation of our project. So for this, we need the sample. So the sample is grown using a conventional solid state reaction technique, which was followed by chemical vapor transport for the single crystals. And I grew the single crystals of around 100 milligram in size, which is one of the biggest single crystals that is available in this material. And this inelastic Newton scattering measurements on single crystals, they are carried out at max NCNR or NIST. Before showing you the elastic data, let me show you the powder average spin excitation spectrum, which I measure at CNCS SNS Oak Ridge National Laboratory. From the powder average data, we can see that the spin excitation spectrum has zone boundary energy around 6 MeV. The zone center looks close to Q is equal to 0, but the resolution limitation of the instrument, we cannot able to look into the dynamics at Q is equal to 0. Once we have some ideas about the spin excitation spectrum from powder average data, I co-aligned some certain number of single crystals with total mass around 1.2 gram along the scattering plane HHL, and the co-alignment is pretty good with the crystal mosaic less than 1.5 degree. And the last figure in this slide, which shows that the temperature dependence intensity, indicating that there is some magnetic scattering at below the magnetic ordering temperature, 13 Kelvin on this temperature, showing some higher intensity at 1.7 K compared to 20K or 50K data. These are the spin waves which I measure from the co-aligned single crystals. The first two figures represent the spin wave along the high symmetry direction 01 and 110 directions. The spin wave along 110 direction, it shows some slopy feature or asymmetry around the zone boundary. And the third figure is the line curves at different region in the reciprocal space, and the last figure in the slide that indicates the constant energy cut, and the circular region shows the constant energy portion of the spin wave cone in this material. For this plot, we took the constant energy 3 MeV. Once you have the data, now we need to visualize the data. For visualization, we need model. For model, I use the Heisenberg, simple Heisenberg spin Hamiltonian with the DM interaction and G momentum. First, I didn't consider the DM interactions, but without adding DM interactions, I couldn't able to reproduce the slopy feature of spin wave along 110 direction. So DM interactions is mandatory at the temperature of 2 Kelvin 2. And for the model, we know in this material that there is a single spin that is associated with the before tetrahedra. So I localize the spin at the center of mass of each tetrahedra, and then model the spin excitation spectrum. By doing this, I could able to reproduce the excitation spectrum, which we measured experimentally. The upper panels shows the theoretically calculated excitation spectrum, and the lower panel, which I showed in the previous slide, that is the experimentally observed spin waves. The spin waves obtained from the model has the same energy scale, and the features are very close, meaning that the model is capable of reproducing the spin excitation spectrum. Based on these simulations, we observed the nearest neighbor exchange coupling around 0.7 MeV, which is strong ferromagnetic, and the DM interaction is around 0.1 MeV, meaning that the DM interaction is around 15% of nearest neighbor exchange interactions in this material. Now I'm showing the line course and the fit of line course along the high symmetry direction 01 and 110. The fitting of constant energy from 2 MeV to 6 MeV along these two high symmetry directions also indicates that the model is completely capturing the feature in this material. What about the powder average data? Does the model replicate the powder average data? Yes. The left hand side and the right hand side represents the experimentally observed and theoretically calculated spin wave spectrum. The zone boundary energy and all the features of excitation spectrum is very close to each other, meaning that the model is reproducing the powder average data too. To check either the model works at field or not, we carried out some inelastic measurements at field, but due to the large background from the magnetic field sample environment, it is hard to compare the zero field and magnetic field data. Although at field of 1 Tesla, we observed that the energy scale is slightly higher compared to the zero field data. These are the outline of my talk. Even the temperature of 2 Kelvin, we observed some fine DM interactions into the system. Thank you for your time. Now I'm open for the questions.
Okay, thank you guys for a nice talk. So we have time for a couple of quick questions. So for Ganesh.
I'm gonna say, I was just wondering, when you show the data from powder, since in powder there is no domain, right? So what do you mean by measuring the spin wave in powder sample?
Oh yeah, yeah. That is the that's why I said like it is a powder average data, meaning that there are multiple domains that they are averaged. So that can give some ideas about the energy scale of interactions inside the system. But exactly to map the action interactions, we need the single crystal data. Single is always very good. So yeah, but even data sometimes we can exactly model the system and get the what is interactions inside the system, but that is not always true because it gives the average. You don't know in what directions what interactions is playing role. So for that we need the single crystal data to look into the particular directions.
So I'm so new to neutron scattering techniques, but it's very impressive that what you can actually do with the neutrons. So can you comment on the domain size? What is the resolution of the technique in terms of how what kind of domain size you can probe?
You can like uh so for that the Newton is basically important to look into the magnetic structure and spin dynamics, magnetic in terms of static structure and dynamic structure. So uh, any material which have the magnetic properties, any kind of magnetic structure, that is good for neutron. But there is like the scattering from the magnetic moment is weaker compared to the nuclear scattering, meaning that x-rays, meaning like that the moment in the system is basically it scatters weaker compared to the nuclear scattering meaning it doesn't contain the information about the magnetic structure. So for Newton scattering measurement we may need little bigger sample because the Newton scatters because of the moment of or the magnetic structure or the magnetic moment from the system. So other than that one, that is a little demerit of Newton scattering. That is, we need little bigger sample. For X-ray, you need like nanocrystal, nano size single crystals or whatever, very small. The mass is also good because it is nuclear scattering. You know the lattice structure from the scattering, but for Newton scattering, you will know about the magnetic structure and spin dynamics. So you may need a little bigger sample because the magnetic scattering is compared to the nuclear scattering, it is weaker. So to scatter neutron, we may need little bigger sample, but Newton scattering is very good probe to study the spin, static and dynamic structure. So once you solve the Newton scattering diffraction data, you will get the static structure, whatever is fermion, blah blah blah, all these magnetic noble exciting the structure you can get Newton scattering because I mean, what I want to say is like Newton scattering is the best probe to look into the spin, static, and dynamic structure. Whatever this skyrmion, all these noble structure, the confirmation about the structure is only people accept or the condensed matter research society they accept the exact result after we have the Newton scattering data, meaning that it is a very very good probe to look into the magnetic structure and spin dynamics. Yeah, but once you have the data, then you can solve all kind of like grain size, the skyrmion, even skyrmion, like conventional magnetic ground state, ferromagnet, antiferromagnetic, all the measurements is yeah you can do it from Newton.
It seems like you saw the domain size of your sample experimentally, directly on your data, right? So what is the domain size that you
Oh,
measured?
sorry. I didn't exactly look into the static structure, meaning that domain size. I look into the dynamic structure
Hmm.
interactions. So I don't have the information about the domain size now.
No, I think you do because you showed the isosurface image, right? In your talk.
Uh, I, s- I mean I know the static structure from literature, but from my measurement, I mean, I didn't exactly. I use the model for the already published static structure
Let
to
me
simulate the.
rephrase this nice Sambu sir's question. What is the length scale that you can probe with Newton scattering? I think is that what you're trying to ask for,
Yeah. What
You
kind of
can
length
you
scale?
can you can measure very long length scale, like even like I mean exact number I don't remember, but like for experiment you have a very
But
large.
in general, you're doing Newton scattering, right? So in general, what
Yes,
is the length scale that you can probe with Newton scattering? Is it, is it a local probe? Is it it is a, it gives average structure. I think
it
that's
gives the
something
average structure. It is not a local probe. You, if you want to look into the local structure, you need muon-spin muon. So it more or less, yeah, gives the average structure on of your system.
Millimeters.
Yeah, millimeter, even in nanometers too. You can go. Yeah, maybe Nirmal sir is the best person to answer if I didn't answer in a right way. Nirmal sir.
No, I'm not a Newton scatter. I'm just
I mean,
trying
I
to
know you have
help
done a lot of work on this one.
get the answer out.
So
Yeah.
sorry for the interruption. With neutrons, you can explore a lot of things, even the local structure, correlation length in angstrom level, atomic level, you can explore. I think the data Ganesh was showing was inelastic data. You should be able to explore what the correlation length in real space is, but maybe that's not the goal of his research. I think he was
Yeah, I can show the correlation length
basically
dynamic structure. Yeah.
Yeah,
Sorry.
as far as what neutrons can do, we can also measure several things like phonons or local structure, any type of magnetic structures like skyrmions or average structure, even the local correlations in the molecules. Yeah, things like that.
Yeah, so that's the after the fact. When you collect data, you go back and then put in your pair distribution functions and things like that, and that is your argument. I guess you can prove the local correlations from there.
Yeah, it's doable, but the technique Ganesh showed was not probably for that. He was showing the dynamics part basically.
Yeah, thanks, Lex,
Sorry
for clarifying.
Okay, so are there more questions for Ganesh? Since you are the last speaker, so you are getting a lot of questions. So don't worry.
That's okay. Yeah, I'm happy. Yeah, it's good conversation. Yeah, especially we want to continue the discussion. Discussion is the major part compared to the talk. Yeah.
Okay. Hi, Ganeshji. I have one question.
Now
Sure.
we have theorist.
Hello. Hello. This is Santos.
Yeah.
Okay.
Hi, Santos. Yeah.
Oh, very nice talk. So I was just interested regarding this material. So you said in a title, it was like multifluoric. So that caught me attention. So can you comment about this? It's polarization, maybe any action restriction mechanism or any spin-driven polarization in this material? Is there any?
Yeah. It has a.
Okay.
Yes. Sorry. Thanks for interrupting. Yeah, it is a multifluoric, like I mentioned, like around like 42 Kelvin. The material is, there is a single spin that occupies the outermost T2 orbital, which is like very orbitally active, meaning that the spin can occupy any state. So the very active behavior results the orbital ordering below 42 Kelvin because of Young-Taylor distortion. So, and that occurs due to the elongation of along the high symmetry 111 direction. That meaning that it induces polarization into the system because it is elongating along particular high symmetry directions. So below the orbital ordering, the material develops polarization into the system. And below 13K, like around 12-13K, the material orders, there is a long range order into the system in terms of magnetic long range order. So at below 13K, you can see the magnetic structure, long range magnetic structure, and even your system is already polarized at little higher temperature. Now at low temperature, you can control the polarization even with the changing the field or changing the magnetic changing the moment inside the system, meaning that you can control the electric polarization from the magnetic field. So yes, it is a multifluoric and yeah, somehow the spin controlled electric polarization too.
Okay, so what do you think? Like, how strong is the coupling in that case?
I am not sure because that will in terms of like the magnetic coupling you're talking about, yeah?
Yeah, so magneto-electronic coupling or electromagnetic coupling, whatever you say, so that you can see this feature, so that you can apply magnetic field and change the polarization, or you apply electric field and change the magnetization. So for that, we need to know the coupling. Is it comparable with other materials such as BF4, bismuth ferrite, or any other?
Probably, I'm not exactly sure how strong it will be, but the already published some literature, they are saying you can control the electric polarization using some like changing the field, but with the field dependence, the coupling, I'm not sure exactly the in magnitude.
Okay, no problem.
How strong?
Yeah, thank you.
Okay, Ganesh, thank you. I think at this point, we are going to stop the session. So I like to thank all the speakers, wonderful talks, and all the attendants for attending and skipping the lunch time. So that's we are really good mixture of good talks in variety of field. And I hope you will continue to tune in and then keep listening and discussing with speakers in upcoming sessions. So like I said, at this point, I'd like to thank you all for attending, participation, and presenting. Thank you all. It was really nice to host this session.
Thank you.
Thank you, Syam sir, and everybody. By the way, we will have AGM in another WebEx link. Please join it. It's going to start very soon. AGM को लागि अर्को लिङ्क छ हैन, सबैजना त्यसमा जोइन भइदिनु होला है त। यो लिङ्क अब हुन्छ, डिएक्टिभेट हुन्छ। सुनियो कि सुनिएन खै? ओके। अर्को लिङ्कमा आउनु होला है त सबैजना। यहाँ लिङ्क तपाईहरुको सजिलोको लागि हुन्छ भने त्यहाँ राख्दै चाहिँ मैले यसमा त्यहाँ जोइन हुन्थे। थ्यांक यू।